Hi, in this video I'm going to explain how we can do a two-phase PSV calculation and size the PSV. In order to size the PSV, we need to define the area, and area is mass flow rate divided by maximum flux times KD times KB. KD and KB are just coefficients and we can select appropriate values for those, but we need to define maximum flux. To determine the maximum flux through a PSV through a nozzle of a PSV, the nozzle is assumed to be isentropic, which is adiabatic and reversible. We need to do a series of isentropic flashes of a relieving fluid starting from the PSV inlet conditions. And from the energy balance for an isentropic flow, we can prove mass flux can be calculated as a square root of -2 times integral of V dP divided by V. Hence, if we need to define mass flux, we need to calculate a specific volumes or mass densities. So we need to calculate mass density as a function of pressure and entropy, which is a constant entropy. And for calculation, we use the midpoint rule, in which we pick the average value between P0 and P1 to calculate the integral. So if you look at the formula here, I have -2000. 1000 is for the unit conversion times E6 minus E5, which is delta P, times H5 plus H6 divided by 2. H5 plus H6 divided by 2 is the average value of the two specific volumes at P0 and P1. So if the specific volume at P0 is V0 and at P1 is V1, we get the average between these two numbers, which is V of P1 star. Here the horizontal axis is P, but in the figure some of these values are shown as X, so X and P are equal. So it's clear from the Excel file that we need to calculate the mass density. There are two methods to calculate mass densities from HYSYS. We can either use a series of expander units, and inside the expander unit, inside the design window, we click on parameters and we enter 100 as the polytropic efficiency, and the number of expanders should be as many as the number of steps, which is 20 in this case. Or there is a shortcut and faster way to do this through adding a property table. I'm going to explain about adding a property table in a second, just after I define the inlet and outlet streams to the PSV. So this is our PSV for the blocked outlet, and the inlet stream is stream 11. We define the temperature, relieving temperature, relieving pressure, and either molar flow or volumetric flow, as well as the compositions. And we can check this stream is liquid and molar entropy is 19.06. This is a constant molar entropy through the isentropic flashes. The outlet stream, if we check, is a two-phase, and we don't define any of the conditions or properties here. They're all automatically calculated. It means the inlet stream is liquid and it flashes as it goes through the PSV. So now if we go to attachments, utilities, we're going to create a new property table, and I click on add utility. Here our specific volume or mass density is a function of entropy and pressure. So we can define our independent variables as entropy, and we set the mode to state, and second is pressure and incremental. So we can enter the state value that we checked earlier on the property window, which was 19.06. This is the constant entropy throughout the flashes. And we define, for pressure, we define lower bound, upper bound, and number of increments. So lower bound is the relieving pressure, which is 250, and upper bound is the destination pressure, which is 18.5, and number of increments is 20, same as what we had in the Excel sheet. Now we have to define our dependent property, which is the mass density. We go down under the variable and we pick mass density, click on OK. Now we can click on calculate, and if we go to the performance tab, we can see mass densities are calculated as a function of, I added the molar density. If we go back to dependent property D, we're going to add mass density. Okay. And then I calculate again. So if I go to the performance, we see that pressures and mass densities are calculated. So now the only thing we need to do is to copy these pressures and paste them into our Excel sheet. And also copy the molar mass density and paste them into our Excel sheet. So based on the mass density, the specific volume, and mass fluxes are calculated, and we get the maximum flux of 33,239. If we put this maximum flux and having the mass flow rate, we can calculate the area of 0.53 square inch, which means we should select orifice H for this application. I just go back to HYSYS to show you the two methods are equivalent. If I go to the last step from the expanders, stream number 33, we can check under properties the mass density is 0.6866. And now if I go back to the performance window or performance tab under utilities, performance, the mass density at the last stage here is also 0.686. So this shows these two methods are equivalent. And that's the end of this video. If you are interested to know more about the basis of this calculation and how we can drive the flux energy from the energy balance for an isentropic flow, you can watch my next video. Thanks.